Welcome students. So, in this lecture we will see an application of derivatives to calculate limits of certain functions. So, more specifically we will learn what is known as the Lopital rules for finding the limit of functions written as ratio of two functions. So, let me state. So, we will learn the Lopital rules. So, this is used to calculate limits of the form limit x approaching c of ratio f x by g x, where c is an extended real number by this we mean that is c is either a real number or plus or minus infinity. So, first let us look at a special case. Suppose f x and g x are continuously differentiable functions in some interval I containing C also assume that f of c is equal to g of c and both are 0, then and let us assume that g prime at c is non-zero. Then we can write f x by g x as f x minus f of c divided by g x minus g of c, since f of c is 0 and g of c is 0, and this we can write as f x minus f of c divided by x minus c over g x minus g of c over x minus c. So, this all these are valid if x belongs to I and x not equal to c. So, now we have written this f x by g x as the ratio of f x minus f c by x minus c and g x minus g c by x minus c. Now, note that what we know is that the limit of f x minus f c by x minus c is nothing but the derivative of f at c. Now, limit x going to c of f x minus f c by x minus c, this is equal to f prime c. Since we have assumed that f is differentiable at c, this limit exists and is equal to the derivative at c, and the limit of x approaching c of g x minus g c divided by x minus c is equal to g prime c. Also, we are assuming that the limit of this denominator, which is g prime c, this is given to be non-zero. So, therefore, limit x going to c of f x minus f c by x minus c over g x minus g c by x minus c, this is nothing but f prime c over g prime c, but this ratio is nothing but f x by g x for x not equal to c. So, therefore, limit of x going to c of f x by g x is equal to f prime c divided by g prime c, but note that this is equal to limit of x going to c of f prime x divided by limit x going to c of g prime x. This is because f prime x and g prime x are assumed to be continuous. Assumed to be continuous at x equal to c. Hence, limit of x going to c of f x by g x is equal to limit of x going to c of f prime x divided by g prime x. So, this above rule which is valid for more general cases is known as the Lopital rule. So, this Lopital is the name of a French mathematician. And this is pronounced as Lopital. So, here H is silent. So, now I will state the Lopital rule in more general situation. Suppose limit of x going to c f x is equal to limit x going to c g x, which is equal to 0 or plus or minus infinity, that is f x by g x limit x going to c. This is of the form 0 by 0 or infinity by infinity. So, if we have this limit in one of these indeterminate form 0 by 0 or plus minus infinity by infinity, then we apply this Lopital rule, and the second assumption is also assume that limit x going to c of f prime x by g prime x, this exists. So, suppose we somehow know that the limit of the ratio of the derivatives of these functions f and g as x approaches c, this limit exists, and we have that g prime x is non-zero for all x in the interval I except possibly at x equal to c. So, we assume that there is some interval in which g prime is non-zero for all x in that interval except maybe at c. Then the conclusion is, then the limit as x approaches c of f x by g x, this exists, and this limit is nothing but the limit of f prime x by g prime x. So, here it is important to note that only if we have this f x by g x is of 0 by 0 or infinity by infinity form, then we can write this limit as the limit of f prime x by g prime x, provided this limit of the right hand side exists. If we do not have limit in 0 by 0 form, we cannot apply this Lopital rule. So, let us see some examples. First example, let me take limit x going to 0 of sin x by x. So, here if we see as x goes to 0, sin x approaches 0 and x approaches 0 also. So, this is of 0 by 0 form. Now, if we look at the limit of x going to 0 of the derivative of sin x by d by dx of x, then this is equal to limit x going to 0, the derivative of sin x if we know is cosine x, and derivative of x is 1. So, we get this is equal to limit of cos x by 1, and the limit of cos x as x approaches 0 is nothing but cos 0 divided by 1. So, this is equal to 1. So, what we got here is that the limit of the derivative this exists and the denominator, if you see the derivative g prime x, this is equal to 1 for all x. So, it is non-zero. So, by the Lopital rule, limit of x going to 0 of sin x by x, this is equal to 1, which we have calculated directly. Note that here we use the fact that the derivative of sin x is cosine x. In fact, if you remember the way we calculated the derivative of sin x is cos x, we used the fact that limit of sin x by x is equal to 1. But suppose you know this fact by some other means, then we can also evaluate the limit of sin x by x equal to 1 using this Lopital rule. Second example, let us look at limit x going to 0 of e to the x minus 1 minus x divided by x square. So, again if I look at this is f x is e to the x minus 1 minus x, g x is x square. At 0, the numerator is 0, denominator is also 0, and both numerator and denominator are continuous functions of x. So, the limit of numerator is 0, the limit of the denominator is 0. So, by applying Lopital rule, this is equal to limit x going to 0 of the derivative of numerator, that will give e to the x minus 1 divided by 2 x. This is by using Lopital rules. Now, if we see this limit, now e to the x minus 1 as x approaches 0 is e to the 0 minus 1, which is 0. So, this is still in 0 by 0 form. So, we can try applying Lopital rule again. So, if we look at now again the derivative of numerator and denominator, we get the derivative of numerator is e to the x, the derivative of denominator is 2. This is again by using Lopital. Now, e to the x is a continuous function. So, this limit is nothing but e to the 0 divided by 2, which is equal to 1 by 2. So, now remark like we see here in this example, here we had to use Lopital rule twice to be able to evaluate the limit. So, we might have to apply Lopital rules several times in order to calculate the limit. Let me mention some complications which can occur. Suppose we try to evaluate limit of x going to infinity of e to the x plus e to the minus x by e to the x minus e to the minus x. So, here we see that as x approaches infinity, e to the x this approaches infinity, e to the minus x approaches 0. So, we get this is of the form infinity by infinity form. So, we might be tempted to use Lopital rule directly. So, if we use Lopital rule, this is equal to limit x going to infinity of derivative of e to the x gives e to the x, derivative of e to the minus x gives minus of e to the minus x, divided by derivative of the denominator gives e to the x plus e to the minus x. Now, if we see again at infinity, the numerator goes to infinity, denominator also goes to infinity. So, it is still of infinity by infinity form. Here I will write in short LH to say that we are applying L'Hopital rule. So, again if I apply L'Hopital rule, we get limit x going to infinity, derivative will give e to the x plus e to the minus x by e to the x minus e to the minus x, which is the original limit itself. So, here we see that by applying L'Hopital rule several times also, we will not be able to calculate this limit. So, we will not be able to calculate the limit by applying L'Hopital rule directly. However, if we put e to the x is equal to y, then as x approaches positive infinity, y approaches infinity, and then the limit becomes e to the x plus e to the minus x by e to the x minus e to the minus x. This is nothing but y plus e to the minus x will be 1 by y minus 1 by y, and this can be written as y square plus 1 by y square minus 1. So, therefore, limit x going to infinity of e to the x plus e to the minus x by e to the x minus e to the minus x is nothing but limit of y going to infinity of y square plus 1 by y square minus 1, which we know how to calculate. We can divide by the highest power y square numerator and denominator, which is equal to limit of y going to infinity of 1 plus 1 by y square by 1 minus 1 by y square, and then this becomes 1 plus 0 by 1 minus 0. So, the limit is 1. Or we can use L'Hopital rule. We could use L'Hopital rule to write limit of y going to infinity y square plus 1 by y square minus 1, this is of infinity by infinity form. So, by L'Hopital we can write this as limit y going to infinity of the derivative of the numerator gives 2 y divided by denominator again gives 2 y, and we can cancel this 2 y and we get this is equal to 1. So, this example shows that sometime we have to do some substitution before applying L'Hopital rule. We can look at another example where applying L'Hopital rule directly will not get anywhere. So, suppose I write square root x plus 1 by square root x divided by square root x minus 1 by square root x. So, this again is of infinity by infinity form, and if we use L'Hopital rule directly, then this will be equal to limit x going to infinity, derivative of square root x gives 1 by 2 square root x plus we have x to the minus half. So, this is minus half x to the minus 3 by 2, then again we have 1 by 2 root x plus half x to the minus 3 by 2. Now, as x goes to infinity, the numerator here goes to 0 and the denominator also both terms goes to 0. So, this is 0 by 0 form. If we apply again L'Hopital rule, we get limit x going to infinity, this is half x to the minus half. So, we get minus 1/4 x to the minus 3 by 2 and then plus this is 3 by 4 x to the minus 5 by 2 by this will be minus 1/4 x to the minus 3 by 2, this becomes minus 3 by 4 x to the minus 5 by 2. This is again 0 by 0 form. So, applying L'Hopital rules makes this expression more and more complicated. Becomes more and more complicated. However, we can write simply limit x going to infinity square root x plus 1 by square root x by square root x minus 1 by square root x, as we can simplify this expression and write this as x plus 1 by x minus 1, and then it is easy to see that this limit is 1 either by dividing numerator and denominator by x, or you can use L'Hopital rule here, and this is limit x going to infinity of the derivative will give 1 by 1. So, this is equal to 1. So, these two examples were to show that you should not apply L'Hopital rule blindly, but try to do some simplification before you apply L'Hopital rule. Now, we will see that this L'Hopital rule can be used for other indeterminate forms like 0 times infinity or infinity minus infinity or 1 to the power infinity, 0 to the power 0, etc., by somehow changing into 0 by 0 or infinity by infinity forms. So, for example, let us first calculate what is limit of x going to infinity of x square times e to the minus x. So, here if we see, as x goes to infinity, x square goes to infinity, e to the minus x goes to 0. So, this is infinity times 0 form, which we have seen is an indeterminate form, but here we have this is a product of two functions and not ratio of two functions. So, to be able to apply L'Hopital rule, first we have to convert it into ratio of two functions. So, we can write this as limit of x going to infinity of x square divided by e to the x. Now, if we see the numerator, it goes to infinity, denominator also goes to infinity. So, we get infinity by infinity form. Therefore, we can apply L'Hopital rule and we get this as limit x going to infinity of the derivative of x square gives 2 x, derivative of e to the x is e to the x. This is still infinity by infinity form. So, we apply L'Hopital rule once more and this gives limit x going to infinity of 2 divided by e to the x. Now, as x goes to infinity, this is numerator goes to 2, denominator goes to infinity. So, this is equal to 0. So, more generally we can show that limit of x going to infinity of x to the n times e to the minus x, this is equal to 0 for any positive integer n. This is because we write this as x to the n divided by e to the x and we keep on applying L'Hopital rule. So, the denominator is always e to the x, when you take derivative you keep getting e to the x, whereas the numerator is x to the n. So, when we take derivative of x to the n, the exponent is reduced by 1. So, if we take derivative n times, then we get a constant in the numerator and denominator is still e to the x, therefore, this limit will be 0. Second example, let us look at limit of x going to 0 from the right of the function x times natural log of x. So, here we are taking the right hand limit because log x is defined here. We are taking limit x going to 0 plus, because log x is defined only for x greater than 0. Now, if we see what happens, this x as x approaches 0 plus we have seen that what happens to log x, this approaches negative infinity. Recall that the graph of log x is like this. At 1 log x is 0, and for x less than 1 the value of log x is negative, and as you keep decreasing the value of x, log x keeps going to negative infinity. So, this limit is of the form 0 times minus infinity. We have to convert this into 0 by 0 or infinity by infinity form. So let us write x log x, this is equal to, we can write this as log x divided by x to the negative 1. Now, this is the numerator goes to negative infinity, denominator goes to positive infinity. So, this is negative infinity by infinity form. So, by Lopital rule, this limit x going to 0 plus of x log x is equal to limit x going to 0 plus of log x by 1 by x, and this, if I use Lopital rule, this is equal to limit x going to 0 plus of derivative of log x gives 1 by x, derivative of 1 by x is minus 1 by x square, and if we simplify this, 1 by x divided by minus 1 by x square is nothing but minus x. So, this is limit x going to 0 plus of minus x, which is equal to 0. So, the limit of x log x as x approaches 0 plus is equal to 0. Let us try to see example where we have the limit of the form infinity minus infinity. So, let us try to calculate limit x going to 0 of 1 by x minus 1 by sin x. So, as x goes to 0, 1 by x approaches plus or minus infinity from right and left, and sin x as x approaches 0 approaches 0. So, this is infinity minus infinity form. Now, here what we can do is we can take the common denominator and write this as sin x minus x divided by x sin x. Now, if we see as x approaches 0, the numerator is approaching 0, and as x approaches 0, denominator is also approaching 0. So, we get 0 by 0 form. So, we can apply L'Hopital rule and write this as limit x going to 0 of the derivative of the numerator gives cos x minus 1 divided by derivative of the denominator, we use product rule and get this as sin x plus x cos x. Now, what happens as x approaches 0, cos x minus 1 was to cos 0 minus 1. So, that is 0, and the denominator has sin x and x cos x. So, this also approaches 0. So, we get 0 by 0 form. So, let us try to apply L'Hopital rule again. If we take the derivative again, we get derivative of cos x is minus sin x divided by derivative of the denominator, sin x derivative is cos x, and x cos x will give plus cos x minus x sin x. Now, if we put x equal to 0, sin 0 is 0, but in the denominator we have cos 0 plus cos 0. This is, let me write down this as minus sin x divided by 2 cos x minus x sin x, and now we get this is equal to 0 divided by 2. So, this is equal to 0. So, we are able to calculate this limit is equal to 0 by using Lopital rule twice after converting this into 0 by 0 form. Now, similarly, we can look at limit of x going to 1 plus of x minus 1 times tan of pi by 2 x. So, as x approaches 1 from the right hand side, x minus 1, this goes to 0, and then we have tan pi by 2 x. So, tan x it goes to infinity, positive infinity as you go to pi by 2 from the left, and from the right this goes to negative infinity. So, here we are taking the limit as x approaches 1 from the right. So, pi by 2 x approaches pi by 2 from the right. So, this is equal to 0 times minus infinity. To be able to use Lopital rule, we should convert it into 0 by 0 or infinity by infinity form. So, let us try to write this as x minus 1 by tan is 1 by cotangent. So, we can write this as cot of pi by 2 x. Now, we get 0 by 0 form. So, if we apply Lopital rule, this is equal to limit x going to 1 plus of derivative of x minus 1 gives 1, derivative of cotangent is minus of cosecant square pi by 2 x times derivative of pi by 2 x is pi by 2. So, we get this, and this is nothing but limit x going to 1 plus of minus 2 by pi times sin square pi by 2 x, because 1 by cosecant is sin, and now as x goes to 1 from the positive side, pi by 2 x goes to pi by 2. So, this is equal to minus 2 by pi times sin square pi by 2, sin pi by 2 is 1. So, this is equal to minus 2 by pi. Another type of limit is, suppose we have 0 by 0 form. So, suppose we write limit of x to the power x as x approaches 0 from the right. So, this is 0 by 0 form. Now, here what we do is, let f x equal to x to the x, then if we take log, natural log of f x is equal to x times natural log of x. Now, what we know is that we have seen that limit x going to 0 plus of x log x this is equal to 0. This we calculated by writing this as log x by 1 by x and then using Lopital rule. This limit is 0. So, therefore, limit of x going to 0 plus of log of f x is equal to 0. What we have to find is what is the limit of f x. So, now f x is nothing but e to the power log f x. So, therefore, limit x going to 0 plus of f x is nothing but limit x going to 0 plus of e to the power log f x, and because exponential is a continuous function, this is equal to e to the power limit x going to 0 plus of log f x. This is because e to the x is continuous. For continuous function, the limit of f of x is same as f of the limit, and now we have already evaluated that this limit is 0. So, this is equal to e to the 0, which is equal to 1. So, this limit is equal to 1. Next, I will show you that the assumption that limit of the ratio of f prime x and g prime x exists is necessary. So, let me write this as a remark. Note that if limit x going to c f prime x by g prime x does not exist, we cannot conclude that the limit of f x by g x does not exist. So, what we have said is that if the limit exists, then the limit f x by g x also exists and they are the same, but even if the limit of f prime x by g prime x does not exist, that does not mean that the limit of f x by g x does not exist. For example, take f x equal to x plus sin x and g x equal to x, then limit x going to positive infinity of f x is equal to infinity, which is also the limit of x going to infinity of g of x. Now, what about f prime x? If we look at f prime x, this is equal to 1 plus cos x, g prime x is equal to 1. So, if we look at f prime x by g prime x, this is equal to 1 plus cos x, so the limit as x going to infinity of this is limit x going to infinity of 1 plus cos x, which does not exist. This is because the limit of cos x at infinity does not exist. Cos x, it keeps oscillating between negative 1 and 1. So, there is no limit as x approaches infinity. However, the limit of x going to infinity of f x by g x, this is equal to limit x going to infinity of x plus sin x divided by x, which is can be written as limit x going to infinity of 1 plus sin x by x. And now, what happens to sin x by x as x approaches infinity? We know that sin x is bounded between negative 1 and 1, denominator x goes to infinity. So, therefore, this sin x by x goes to 0. So, sin x by x in mod is less than equal to 1 by x and greater than equal to 0, and 1 by x, this goes to 0 as x approaches infinity. So, we have seen that by the sandwich theorem, limit x going to infinity of sin x by x, this is equal to 0. Therefore, limit of x going to infinity of f x by g x is equal to 1 plus 0, which is equal to 1. Though if we directly try to use Lopital rule, then we get the limit of f prime x by g prime x, which does not exist, but that does not mean that this original limit does not exist. So, with this I will stop this lecture. Thank you.